Very happy to see you guys again. Here we are going to the chapter 6. Building your first deep neural network. Introduction to backpropagation. In this chapter, we will know the straight line problem, matrices, and the metric relationship, for Bayes and stochastic gradient descent, neural networks null correlation, overfitting, creating your own correlation, backpropagation, long-distance error attribution, linear versus nonlinear, the secret to sometimes correlation. Your first deep neural network, backpropagation in code. Bring it all together. Oh, deep thought computer, he said, the task we have designed you to perform is this. We want you to tell us, he paused, the answer. The straight line problem. This type problem considers how a network learns entire datasets. Consider yourself approaching a street corner in a foreign country. As you approach, you look up and realize that the street light is unfamiliar. How can you know when it's safe to cross the street? You can know when it's safe to cross the street by interpreting the street light. But in this case, you don't know how to interpret it. Which light combinations indicate when it's time to work, which indicate when it's time to stop. To solve this problem, you might sit at the street corner for a few minutes, observing the correlation between each light combination and whether people around you choose to work or stop. You take a set and record the following pattern. If the street light acts like something like this, okay, nobody walked at the first night. At this point, you're thinking, well, this pattern could be anything. The left light or the right light could be correlated with stopping, or the central light could be correlated with walking. There's no way to know it. Let's take another data point. For example, this kind of a view. People walked, so something about this light changed the signal. The only thing you know for sure is that the far right light doesn't seem to indicate one way or another. Perhaps it's irrelevant. Let's collect another data point. Now you're getting somewhere. Only the middle light changed this time, and you got the opposite pattern. The working hypothesis is that the middle light indicates when people feel safe to work. Over the next few minutes, you record the following 6 light patterns. Nothing when people work or stop. Do you notice a pattern overall? So if I was that man, I would say, okay, I'll just work when others start to work. I won't consider that much. As hypothesized, there is a perfect correlation between the middle light and whether it's safe to work. You learn this pattern by observing all the individual data points and searching for correlation. This is what you are going to train a neural network to do. Preparing the data. Neural networks doesn't read straight lines. In the previous chapters, you learned about supervised algorithms. You learned that they can take one dataset and turn it into another. More important, they can take a dataset of what you know and turn it into a dataset of what you want to know. How do you train a supervised neural network? You present it with 2 datasets and ask it to learn how to transfer one into the other. Think back to the straight line problem. Can you identify 2 datasets? Which one do you always know? Which one do you want to know? You do indeed have 2 datasets. One on the one hand, you have 6 straight line states. One on the other hand, you have 6 observations of whether people worked. There are the 2 datasets. You can train the neural network to convert from the dataset you know to the dataset that you want to know. In this practical real-world example, you know the state of the street light at any given time, and you want to know whether it's safe to cross the street. Here's what you know on the left side, and here's what you want to know on the right side. To prepare this data for the neural network, you need to first split it into these 2 groups, what you know and what you want to know. Note that you could attempt to go backward a few swaps, which dataset was in which group. For some problems, this works. Matrices and the metric relationship. Translate the streetlight into math. Math doesn't understand streetlights. As mentioned in the previous section, you want to teach a neural network to translate a streetlight pattern into the correct stop work pattern. This operative word here is pattern. What you really want to do is mimic the pattern of the streetlight in the form of numbers. Let me show you what I mean. Okay, he just translated the streetlight's graph into a bunch of vectors of 0 or 1. Notice that the pattern of numbers shown here mimics the pattern from the streetlights in the form of 1s and 0s. Each light gets a clone. 3 clones total, because there are 3 lights. Notice also that there are 6 rows representing the 6 different observed streetlights. This structure of 1s and 0s is called a matrix. The relationship between the rows and clones is common in matrices, especially matrices of data like the streetlights. In data matrices, it's convention to give each recorded example a single row. It's also convention to give each scene being recorded a single clone. This makes the matrix easy to read. So a clone contains every state in which a scene was recorded. In this case, a clone contains every on or off state recorded for a practical light. Each row contains the simultaneous state of every light at a practical moment in time. Again, this is common. Good data matrices perfectly mimic the outside world. The data matrix doesn't have to be all 1s or 0s. What if the streetlights were on dimers and turned on and off at varying degrees of intensity? Perhaps the streetlight matrix would look more like this. The matrix A is perfectly valid. It's mimicking the patterns that exist in the real-world streetlight, so you can ask the computer to interpret pattern. Would the following matrix still be valid? Matrix B is valid. It adequately captures the relationships between various trailing examples, rows, and the lights clones. Note that the matrix A times 10 equal to matrix 10 equal to the matrix B. This means these matrices are scalar multiples of each other. Matrices A and B both contain the same underlying pattern. The important takeaway is that an infinite number of matrices exist that perfectly reflect the streetlight patterns in the dataset. Even the one shown next is perfect. It's important to recognize that the underlying pattern isn't the same as the matrix. It's a property of the matrix. In fact, it's a property of all 3 of these matrices, A, B, and C. The pattern is what each of these matrices is expressing. The pattern also existed in the streetlights. This input data pattern is what you want the neural network to know to transfer into the output data pattern. But in order to know the output data pattern, you also need to capture the pattern in the form of a matrix, as shown here. The stop equal to 0, the work equal to 1. Note that you could reverse the ones and zeros, and the output matrix would still capture the underlying stop or work pattern that's present in the data. You know this because regardless of whether you send a 1 to work or to stop, you can still decode the ones and zeros into the underlying stop or work pattern. The resulting matrix is called a lossless representation because you can perfectly convert back and forth between your stop or work nodes and the matrix. Creating a matrix or two in Python. Import the matrices into Python. You converted the straight-line pattern into a matrix, one with just 1 and zeros. Now let's create the matrix, and more importantly, its underlying pattern in Python so the neural network can read it. Python's NumPy library, introduced in Chapter 3, was built just for handling matrices. Let's see it in action. Here is it. We can import NumPy as NP, and the straightlines would be equal to NumPy.array with the matrix. If you are a regular Python user, something should be stricken in this code. A matrix is just a list of lists. It's an array of arrays. What is NumPy? NumPy is really just a fancy wiper for an array of arrows that provides special matrix-oriented functions. Let's create a NumPy matrix for the output data, too. It's something like this. What do you want the neural network to do? Take the straightlines matrix and know to transfer it into the work vs stop matrix. More important, you want the neural network to take any matrix containing the same underlying pattern as straightlines and transfer it into a matrix that contains the underlying pattern of work vs stop. More on that later. Let's start by trying to transfer straightlines into work vs stop using a neural network. Building a neural network. You'll be learning about neural networks for several chapters now. You have a new dataset, and you are going to create a neural network to solve it. Following is some example code to know the first straight-line pattern. That should look familiar. Okay, first we import NumPy as NP. The whites equal to NumPy.array with the array. Actually, in the real world, we couldn't know the weights by advance. The alpha equal to 0.1, the straightlines equal to something like that, and the work with the stop, the output equal to something like this. The input equal to straightlines, the first elements of the straightlines. The goal prediction equal to the first element of work with stop matrices. For iteration in range 20, we will run those codes for 20 times. The prediction equal to the input dot the weights. The error equal to the goal prediction minus the prediction squared. The data equal to the prediction minus the goal prediction. The weights equal to the weights minus the alpha times the input times the data. This code example may bring back several nuances you learned in Chapter 3. First, the use of the dot function was a way to perform a dot product weighted sum between two vectors, but not included in Chapter 3 was the way NumPy matrix can perform element-wise addition and multiplication. NumPy makes these operations easy when you put a plus between two vectors. It does what you expect. It adds the two vectors together. Other than this nonce these slice NumPy operators and the new dataset. The neural network shown here is the same as the ones built previously. Learning the whole dataset. The neural network has been learning only one streetlight. Don't we want it to learn them all? So far in this book, you trained neural networks that learned how to model a single training example, the input to the goal prediction pair. But now you are trying to build a neural network that tells you whether it's safe to cross the street. You need to know more than one streetlight. How do you do this? You train it on all the streetlights at once. We import NumPy as NP, the weights equal to NumPy.array with that, the alpha equal to this. The streetlights equal to NumPy.array with that. The work with stop NumPy.array is something like that. We still got the first element as the input and the output. For iteration in range 14, we're gonna run those code for 40 times. Error for all lights equal to 0. For row indexed in range, the length of work with stop, the input equal to the streetlights row indexed. The goal prediction equal to the work with stop row indexed. The prediction equal to the input dot the weights. The error is the same. The error for all lights is we're gonna add all error together. The data equal to prediction minus the goal prediction. The weights equal to the same. Okay, in here, in this version of code, the author just used a for loop to iterate the streetlights row. For beige and stochastic gradient descent. Stochastic gradient descent updates weights one example at a time. As it turns out, this idea of learning one example at a time is a variant on gradient descent called stochastic gradient descent, and it's one of the handful of methods that can be used to learn an entire dataset. How does stochastic gradient descent work? As you saw in the previous example, it performs a prediction and weight update for each training example separately. In other words, it takes the first streetlight, tries to predict it, calculates the weight data, and updates the weights. Then it moves on to the second streetlight and so on. It iterates through the entire dataset many times until it can find a weight configuration that works well for all the training examples. For gradient descent updates weights one dataset at a time. As introduced in Chapter 4, another method for learning an entire dataset is gradient descent, or average or full gradient descent. Instead of updating the weights once for each training example, the network calculates the average weight data over the entire dataset, changing the weights only each time it computes a full average. Bench gradient descent updates weights after n examples. This will be covered in more detail later, but there's also a third configuration that sort of splits the difference between the stochastic gradient descent and full gradient descent. Instead of updating the weights after just one example or after the entire dataset of examples, you choose a batch size, typically between 8 and 246 of examples, after which the weights are updated. We will discuss this more later in this book, but for now, recognize that the previous example created a neural network that can learn the entire streetlights dataset by training on each example once at a time. Neural networks learn correlation. What did the last neural network learn? You just got done training a single layer neural network to take a straight line pattern and identify whether it was safe to cross the street. Let's take on the neural network's perspective for a moment. The neural network doesn't know that it was processing streetlight data. All it was trying to do was identify which input of the three possible correlated with the output. It correctly identified the middle lights by analyzing the final weight positions of the network. Notice that the middle weight, here you can say the middle weight, is nearly 1, whereas the far left and the far right weights are very near to 0. At a high level, all the interactive, complex process for learning accomplished something rather simple. The network identified correlation between the middle input and the output. The correlation is located whether the weights were set to high numbers. Inversely, randomness with respect to the output was found at the far left and the far right weights, where the weight values are very near to 0. How did the network identify correlation? Well, in the process of gradient descent, each training example asserts either up pressure or down pressure on the weights. On average, there was more up pressure for the middle weights and more down pressure for the other weights. Where does the pressure come from? Why is it different for different weights? Up and down pressure. It comes from the data. Each node is individually trying to correctly predict the output given the input. For the most part, each node ignores all the other nodes when attempting to do so. The only cross-communication occurs in the all three weights must share the same error measure. The weight update is nothing more than taking this shared error measure and multiplying it by each respective input. Why do you do this? A key part of why neural networks learn is error attribution, which means given a shared error, the network needs to figure out which weights contributed, so they can be adjusted and each weight did not contribute to the errors, so they can be left alone. Here's the training data and here's the weight pressure. Alright, consider the first training example. Because the middle input is 0, the middle weight is completely irrelevant for this prediction. No matter what the weight is, it's going to be multiplied by 0, the input. Thus, any error that at the training example, regardless of whether it's too high or too low, can be attributed to only the far left and the right weights. Consider the pressure of this first training example. If the network should predict 0 and the two inputs are 1s, then this will cause error, which drives the weight values toward 0. The weight pressure table helps describe the effect of each training example on each respective weight. The plus indicates that it has pressure toward 1, and the negative sign indicates that it has pressure toward 0. Zeros indicate that there is no pressure because the input data point is 0. So that weight won't be changed. Notice that the far left weight has 2 negatives and 1 positive. So on average, the weight will move toward 0. The middle weight has 3 positives, so on average, the weight will move toward 1. Each individual weight is attempting to compensate for error. In the first training example, there's a discorrelation between the far right and far left inputs and the desired output. This causes those weights to experience down pressure. This same phenomenon occurs throughout all 6 training examples, regarding correlation with pressure toward 1 and penalizing discorrelation with pressure toward 0. On average, this causes the network to find the correlation present between the middle weight and the output to be the dominant predictive force, Harris weight in the weighted average of the inputs, making the network quite accurate. Bottom line, the prediction is a weighted sum of the inputs. Great. The learning algorithm rewards inputs that correlate with the output with upward pressure toward 1 on the weights, while penalizing inputs with discorrelation with downward pressure. The weighted sum of the inputs find the perfect correlation between the input and output by weighting decorrelated inputs to 0. The mathematician in you may be grabbing a leg. Upward pressure and downward pressure are hardly precise mathematical expressions, and they have plenty of edge cases where this logic doesn't hold, which we will address in a second. But you'll later find that this is an extremely valuable approximation, allowing you to temporarily overlook all the complexity of gradient descent and just remember that learning rewards correlation with large weights, and more generally, learning finds correlation between the two datasets. Edge case overfitting. Sometimes correlation happens accidentally. Consider again the first example in the training data. What if the far left weight was 0.5 and the far right weight was negative 0.5? The prediction would equal to 0. The network would predict perfectly, but it hasn't remotely learned how to safely predict streetlights. These streetlights would fall in the real world. This phenomenon is known as overfitting. Deep learning's greatest weakness is the overfitting. Error is shared among all the weights. If a particular configuration of weights accidentally creates perfect correlation between the prediction and the output dataset, such that error equal to 0 without giving the highest weight to the best inputs, the neural network will stop learning. If it wasn't for the other training examples, this fatal flaw would cripple the neural network. What do the other training examples do? Well, let's take at the second training example. It bumps the far right weight upward while not changing the far left weight. This throws off the equilibrium that stopped the learning in the first example. As long as you don't train exclusively on the first example, the rest of the training examples will help the network avoid getting stuck in these edge case configurations that exist for any one training example. This is very important. Neural networks are so flexible that they can find many different weight configurations that will correctly predict for a subset of training data. If you trained this neural network on the first two training examples, it would likely stop learning at a point where it did not work well for the other training examples. In essence, it memorized the two training examples instead of finding the correlation that will generalize to any possible streetlight configuration. If you train on only two streetlights and the network finds just these edge case configurations, it could fail to tell you whether it's safe to cross the street when it sees a streetlight that wasn't in the training data. Key takeaway: the greatest challenge you'll face with deep learning is convincing your network to generalize instead of just memorize. You'll say this again, okay? It's the same when human learns. At the most of the time, human will try to memorize things instead of generate common rules. That's a big problem for learning. So we don't want to, get some people like he just memorizing anything. That's not good because it will not work in real world. The real world will change as the time grows. Edge case, conflicting pressure. Sometimes correlation fights itself. Consider the far right column in the following weight pressure table. What do you say? This column seems to have an equal number of upward and downward pressure moments, but the network correctly pushes this far right weight down to 0, which means the downward pressure moments must be larger than the upward ones. How does this work? The left and the middle weights have enough signal to coverage on their own. The left weight falls to 0, and the middle weight moves toward 1. As the middle weight moves higher and higher, the arrow for positive examples continues to decrease. But as they approach their optimum positions, the decorrelation on the far right weight becomes more apparent. Let's consider the extreme example where the left and middle weights are perfectly set to 0 and 1, respectively. What happens to the network if the right weight is above 0? Then the network produces too high, and if the right weight is beneath 0, the network produces too low. As other nodes learn, they absorb some of the error. They absorb part of the correlation. They cause the network to predict with moderate correlative power, which reduces the error. The other weights then only try to adjust their weights to correctly predict what's left. In this case, because the middle weight has consistent signal to absorb all the correlation because of the one-with-one relationship between the middle input and the output, the error when you want to predict 1 becomes very small, but the error to predict 0 becomes large, pushing the middle weight downward. It doesn't always work out like this. In some ways, you kind of got lucky. If the middle node hadn't been so perfectly correlated, the network might have struggled to silence the far right weight. Later, you'll learn about regularization, which forces weights with conflicting pressure to move toward 0. As a preview, regularization is advantageous because if a weight has equal pressure, upward and downward, it isn't good for anything. It's not happy in either direction. In essence, regularization aims to say that only weights with really strong correlation can stay on. Everything else should be silenced because it's contributing noise. It's sort of like neural selection, and as a side effect, it would cause the neural network to train faster, fewer iterations, because the far right weight has this problem of both positive and negative pressure. In this case, because the far right node isn't identifiably correlative, the network would immediately start driving it toward 0. Without regularization, as you trained it before, you wouldn't end up learning that the far right input is until is useless. You wouldn't end up learning that the far right input is useless until after the right and middle start to figure out their patterns. More on this later. If networks look for correlation between an input column of data and the output column, what would the neural network would do with the following dataset? There is no correlation between any input column and the output column. Every weight has an equal amount of upward pressure and downward pressure. This dataset is a real problem for the neural network. Previously, you could solve for input data points that had both upward and downward pressure because other nodes would start solving for either the positive or negative predictions, driving the balanced node to favor up or down. But in this case, all the inputs are equally balanced between positive and negative pressure. What do you do? Learning indirect correlation. If your data doesn't have correlation, create intermediate data that does. Previously, I described a neural network as an instrument that searches for correlation between the input and output datasets. I want to refine this just a touch. In reality, neural networks search for correlation between the input and output layers. You set the values of the input layer to be individual rows of the input data, and you try to train the network so that the output layer equals the output datasets. Oddly enough, the neural network doesn't know about data. It just searches for correlation between the input and output layer. Unfortunately, this is a new serialized dataset that has no correlation between the input and output. The solution is simple. Use two of these networks. In the first one, we'll create an intermediate dataset that has limited correlation with the output. And the second will use the limited correlation and to correctly predict the output. Because the input doesn't correlate with output dataset, you'll use an input dataset to create an intermediate dataset that does have correlation with output. It's kind of like cheating. Creating correlation. Here's the picture of the new neural network. You basically stack two neural networks on top of each other. The middle layer of nodes, layer 1, represents the intermediate dataset. The goal is to train this network so that even though there's no correlation between the input dataset and output dataset, the layer 0 and the layer 2, the layer 1 dataset that you create using layer 0 will have correlation with layer 2. So here we can see a picture of layers. And at the center of this graph, you will see the immediate layer. Note that this network is still just a function. It has a bunch of weights that are collected together in a particular way. Furthermore, gradient descent still works because you can calculate how much each weight contributes to the error and adjust it to reduce the error to 0. And that's exactly what you are going to do. Stacking neural networks, a review. Chapter 3 briefly mentioned stacked neural networks. Let's review. When you look at the following architecture, the prediction occurs exactly as you might expect when I say stack neural networks. The output of the first neural network, the layer 1 and layer 0, is the input to the second upper neural network, layer 1 and layer 2. The prediction for each of these networks is identical to what you saw before. As you start to think about how this neural network learns, you already know a great deal. If you ignore the neural weights and consider their output to be the training set, the top half of the neural network, the layer 1 and layer 2, is the toppest layer in this network. It's just like the networks trained in the preceding chapter. You can use all the same learning logic to help them learn. The part that you don't yet understand is how to update the weights between layer 0 and layer 1. What do they use as their error measure? As you might remember from chapter 5, the cached or normalized error measure is called delta. In this case, you want to figure out how to know the delta values at layer 1 so they can help layer 2 make accurate predictions. So that will introduce us a new idea. Backpropagation, long distance error attribution, the weighted average error. What's the prediction from layer 1 to layer 2? It's a weighted average of the values at layer 1. If layer 2 is too high by X amount, how do you know which values at layer 1 contributed to the error? The ones with higher weights, layer 1 2, contributed more. The ones with lower weights from layer 1 to layer 2 contributed less. Consider the extreme. Let's say the far left weights from layer 1 to layer 2 was 0. How much did that node at layer 1 causes the network's error? 0. It's so simple, it's almost hilarious. The weights from layer 1 to layer 2 exactly describe how much each layer 1 node contributes to layer 2 prediction. This means those weights also exactly describe how much each layer 1 node contributes to the layer 2 error. How do you use the data at layer 2 to figure out the data at layer 1? You multiply it by each of the respective weights for layer 1. It's like the prediction logic in reverse. This process of moving data signal around is called backpropagation. Okay, we can see it from here. The layer 1 data which are actually weighted versions of the layer 2 data. The value is the layer 2 data core prediction minus the prediction. I made up some weight values so you can see how the layer 2 data passes through them. I don't know what he was talking about. Backpropagation. Why does this work? The weighted average data. In the neural network from chapter 5, the data variable told you that the direction and amount the value of this node should change next time. Or backpropagation lets you do is say, hey, if you want this node to be X amount higher, then each of these previous 4 nodes need to be X times weights 1 2 amount higher or no, because these weights were amplifying the prediction by weights 1 2 times. When used in reverse, the weights 1 2 matrix amplifies the error by the upright amount. It amplifies the error so you know how much each layer 1 node should move up or down. Once you know this, you can update each weight matrix as you did before. For each weight, multiply its output data by its input value and adjust the weight by that much, or you can scale it with alpha. I bet it's not necessary to understand the whole stuff on backpropagation. At least for now, I don't think it's necessary. Learning vs non-linear vs non-linear. This is probably the hardest concept in the book. Let's take it slowly. I'm going to show you a phenomenon. As it turns out, you need one more piece to make this neural network train. Let's take it from 2 perspectives. The first will show why the neural network can't train without it. In other words, first I'll show you why the neural network is correctly broken. Then once you add this piece, I'll show you what it does to fix this problem. For now, check out this simple algebra. Here's the takeaway. For any 2 multiplications, I can accomplish the same thing using a single multiplication. As it turns out, this is bad. Check out the following. These 2 graphs show 2 training examples each. One where the input is 1.0 and another where the input is negative 1.0. The bottom line, for any 3-layer network you create, there's a 2-layer network that has identical behavior. Stacking 2 neural networks as you know them at the moment doesn't give you any more power. 2 consecutive weighted sum is just more expensive version of one weighted sum. What's that? Why the neural network still doesn't work? If you train the 3-layer network as it is now, it won't converge. For any two consecutive weighted sums of the input, there exists a single weighted sum with exactly identical behavior. Anything that the 3-layer network can do, the 2-layer network can also do. Okay, now I understand. It is said that if it's a linear layer of 3 layers, we could do the same thing with 2 layers. Let's talk about the middle layer, layer 1, before it's fixed. Right now, each node out of the 4 has a weight coming to it from each of the inputs. Let's think about this from a correlation standpoint. Each node in the middle layer subscribes to a certain amount of correlation with each input node. If the weight from an input to the middle layer is 0.1, then it subscribes to exactly 100% of the node's movement. If that node goes up by 0.3, the middle node will follow. If the weight connection to nodes is 0.5, each node in the middle layer subscribes to exactly 50% of the node's movement. The only way the middle node can accept the correlation of one particular input node is if it subscribes to additional correlation from another input node. Nothing new is being contributed to this neural network. Each hidden node subscribes to a lead correlation from the input nodes. The middle nodes don't get to add anything to the conversation. They don't get to have the correlation of their own. They are more or less correlated to various input nodes. But because you know that in the new dataset there is no correlation between any of the inputs and the outputs, how can the middle layer help? It mixes up a bunch of correlation that's already useless. What you really need is for the middle layer to be able to selectively correlate with the input. You want the middle layer to sometimes correlate with an input and sometimes not correlate. That gives it correlation of its own. This gives the middle layer of the opportunity to not just always be X% correlated to one input and 1% correlated to another input. Instead, it can be X% correlated to one input only when it wants to be, but other times not be correlated at all. This is called a conditional correlation or sometimes correlation. Okay, it's hard. What he was talking about, it's nothing to me. I can't follow clue of what he saying. The secret to sometimes correlation. Turn off the node when the value would be below 0. This might seem too simple to work. But consider this, if a node's value dropped below 0, normally the node would still have the same correlation to the input as always. It would just happen to be negative in value. But if you turn off the node, setting it to 0 when it would be negative, then it has zero correlation to any inputs whenever it's negative. What does this mean? The node can now selectively pick and choose when it wants to be correlated to something. This allows it to say something like this: make me perfectly correlated to the left input, but only when the right input is turned off. How can it do this? Well, if the weight from the left input is 1.0 and the weight from the right input is a huge negative number, then turning on both the left and right inputs will cause the node to be 0 all the time. But if only the left input is on, the node will take on the value of the left input. This wasn't possible before. Earlier, the middle node was either always correlated to an input or always not correlated. Now it can be conditional. Now it can speak for itself. Solution: by turning off any middle node whenever it would be negative, you allow the network to sometimes subscribe to the correlation from various inputs. This is impossible for two-layer neural networks, thus adding power to three-layer nodes. The fancy term for this, if the node would be negative, set it to 0. Logic is nonlinearity. Without this trait, the neural network is linear. Without this technique, the output layer only gets to pick from the same correlation it had in the two-layer network. It's subscribing to pieces of the input layer, which means it can't solve the new straight-line dataset. There are many kinds of non-linearities, but the one discussed here is, in many cases, the best one to use. It's also the simplest. It's called ReLU. For what it's worth, most other books and courses say that consecutive matrix multiplication is a linear transformation. I found this unintuitive. It also makes it hard to understand what non-linearity contributes and why you choose one over the other, which we will get to later. It says without the non-linearity, two matrix multiplications might as well be one. My explanation, although not the most concise answer, is an intuitive explanation of why you need non-linearities. Okay, I don't think this is good to explain this scene with that much text or distributions or descriptions. I think it's more reasonable for you to say that we use ReLU because it will allow the network to learn new stuff instead of stuck in the old pattern. That will make more sense for me, I guess. A quick break. That last part probably felt a little abstract, and that's totally okay. Here's the deal. Previous chapters worked with simple algebra, so everything was ultimately grounded in fundamentally simple tools. These chapters started building on the promises you learned earlier. Previously, you learned lessons like this. You can compute the relationship between the error and any one of the weights so that you know how changing the weight changes the error. You can then use this to reduce the error to 0. That was a massive lesson. But now we are moving past it because we already worked through why that works. You can take the statements at face value. The next big lesson came at the beginning of this chapter. Adjusting the weights to reduce error over a series of training examples ultimately searches for correlation between the input and output layers. If no correlation exists, then the error will never reach 0. This is an even bigger lesson. It largely means you can put the previous lesson out of your mind for now. You don't need it. Now you are focused on correlation. The takeaway is that you can't constantly think about everything all at once. Take each lesson and let yourself trust it. When it's a more conscious summarization, a higher abstraction of more granular lessons, you can set aside the granular and focus on understanding the higher summarizations. This is akin to a professional swimmer, biker, or seminar athlete who requires a combined fluid knowledge of a bunch of small lessons. A baseball player who swings a bat learned thousands of lead lessons to ultimately culminate in a great bat swing. But the player doesn't think of all of them when he goes to the plate. His actions are fluid, even subconscious. It's the same for studying. these math concepts, neural networks look for correlation between input and output, and you no longer have to worry about how that happens. You just know it does. Now we are building on that idea. Let yourself relax and trust the things you already learned. Your first deep neural network. Here's how to make the predictions. For this, I'm going to type those code by myself in the notebook, so I can learn this stuff quickly. Okay, I just did that type in my chapter notebook. Maybe we can have a look at this. First, he just imported the NumPy as NP, then he set the written set to 1. He defined the ReLU function with S. So what this function does is to set all negative numbers to 0. So I don't know why how he achieved that by using this line of code. I have no idea about that. Then he just set the alpha equal to 0.2, the hidden size equal to 4. Then he defined the weights by using real numbers. Then he defined the first layer, which is the input. Then he just used the ReLU to calculate the np.layer0 times the weights. Then he used another layer to by using he got the layer 2 by using np.layer1 times the weights 1, 2. The output of layer 1 is sent to ReLU, where negative values become 0. This is the input for the next layer, layer 2. So at least we can know one thing from this code. That is, the previous layer's output is the input for the following layer. For each piece of the code, follow along with the figure. Input data comes into layer 0. While the dot function, the signal travels up the weights from layer 0 to layer 1, performing a weighted sum at each of the 4 layer 1 nodes. These weighted sums at layer 1 are then passed through the ReLU function, which converts all negative numbers to 0. Then, the final weighted sum is performed into the final node, layer 2. Backpropagation in code, you can learn the amount that each weight contributes to the final arrow. At the end of the previous chapter, I made an assertion that it would be important to memorize the 2-layer neural network code, so you could quickly and easily recall it when I reference more advanced concepts. This is when that memorization matters. The following lasting is the new learning code, and it's essential that you recognize and understand the parts addressed in the previous chapters. If you get lost, go back to chapter 5, memorize the code, and then come back. It will make a big difference someday. So you'd better pause this video and try to type those code as I did. Okay, here's what I did. I just did a lot of typing work in here. Here's what I found. Here he just defined another function here. It returns 1 for input greater than 0. Returns ill otherwise. Then he just defined 2 layers. The first layer with the weights 0, 1. The second layer with the weights 1, 0, 2. We can ignore the iteration here. We don't have to understand it. But the first we define the layer 2 arrow. it is equal to 0. For I in the range of the length of the straight lines, we iterate the rows. The layer 0 equal to the straight lines, the first row, for example, the first row, the I with the I plus 1 as a slash to get the current row of that of our input data or output data. The layer 1 equal to ReLU np dot times the layer 0 and the weights, the first layer weights. It is the same as we have seen in the previous code, in the previous chapter codes. Then we define the layer 2 again with lampy dot function. This time we times the layer 1, which is the layer 1 output, to the layer 2 weights, because we have to, because we want to calculate the layer 2 outputs, so we have to use the inputs times the layer 2 weights. Okay, how we get the layer 2 arrow? It is simple. We use a function lampy.sum. Again, it is the same as we have seen in the previous chapter. We use layer 2 minus the final output, the goal prediction. We get the error and we square it. Okay, then the layer 2 delta. How do we get that? It's still the same. We use the goal prediction. We use the final real value to minus the layer 2, because the layer 2 is a final layer of our network. Then how do we get the layer 1 delta? It is calculated by using the layer 2 delta dot the weights of layer 2. Okay, it's just one of this family. It's just one of this family. We instead despite of using the layer 2 values, we will still using the layer 1 values. Okay, so how do we do that? We just using a dot function or a dot operator to do that, and also the ReLU new function here, we return that. So anyway, all those operations are based on matrices. It's no longer a single value at all. It's a matrix. Every operation are based on matrix, are calculated with matrix. And finally, we use the delta to change the real weights by using this. It is the same as we seen in the previous chapter. We calculate the layer 2 weights by using layer 1 times the layer 2 delta. We calculate the layer 1 weights by using the layer 0 times the layer 1 delta. Believe it or not, the only truly new code is in blood. Everything else is fundamentally the same as in previous pages. The ReLU2 DRIV function returns 1 when the output greater than 0, otherwise it returns 0. This is the slope, the derivative of the ReLU function. It serves an important purpose, as you'll see in a moment. Remember, the goal is error attribution. It's about figuring out how much each weight contributed to the final error. In first two-layer neural network, you calculated a delta variable, which told you how much higher or lower you wanted the output prediction to be. Look at the code here. You compute the layer 2 delta in the same way, nothing new. Again, go back to chapter 5 if you have forgotten how that part works. Now that you know how much the final prediction should move up or down by the delta, you need to figure out how much each mid-layer node should move up or down. These are effectively intermediate predictions. Once you have the data at layer 1, you can use the same processes as before for calculating a weight update. For each weight, multiply its input value by its output data and increase the weight value by that much. How do you calculate the data for layer 1? First, do the obvious, multiplying the output data by each weight attached to it. This gives a weighting of how much each weight contributed to that error. There's one more thing to factor in. If ReLU set the output to a layer 1 node to be 0, then it didn't contribute to the error. When this is true, you should also set the data of that node to 0. Multiply each layer 1 node by the ReLU2 DRI wave function. Accomplishes this. This function is either 1 or 0, depending on whether the layer 1 value is greater than 0. The value is a layer 2 data, goal prediction minus a prediction. I made up some weight values so you can see how the layer 2 data passes through them. Layer 1 data, which are actually weighted version of the layer 2 data. One iteration of backpropagation. Here's the inputs, the hidden layers, the predictions. Predict plus compare, making a prediction and calculating the output error and data. Backpropagating from layer 2 to layer 1. Generating weight data and updating weights. As you can see, backpropagation is about calculating data for intermediate layers so you can perform gradient descent. To do so, you take the weighted average data on layer 2 for layer 1, weighted by the weights in between them. You then turn off set to 0 nodes that wasn't participating in the forward prediction because they couldn't have contributed to the error. Putting it all together, here's a self-sufficient program you should be able to run. Runtime output follows. It's the same as we have seen earlier, the code. Okay, if I run that code, I'll get the same result as the other did. Why do deep learning networks matter? What's the point of creating intermediate datasets that have correlation? Consider the cat picture shown here. Consider further that I had a dataset of images with cats and without cat, and I labeled them as much. If I wanted to train a neural network to take the pixel values and predict whether there's a cat in the picture, the two-layer network might have a problem. Just as in the last streetlight dataset, no individual pixel correlates with whether there's a cat in the picture. Only different configurations of pixels correlate with whether there's a cat. This is the essence of deep learning. Deep learning is all about creating intermediate layers or datasets, wherein each node in an intermediate layer represents the presence or absence of a different configuration of inputs. This way, for the cat images dataset, no individual pixel has to correlate with whether there's a cat in the photo. Instead, the middle layer will attempt to identify different configurations of pixels that may or may not correlate with a cat, such as an ear or cat eyes or cat hair. The presence of many cat-like configurations will then give the final layer the information or correlation it needs to correctly predict the presence or absence of a cat, so whether there's a cat in that image. So I'll explain that in another way for you. If we only use one layer of neural networks, every pixels will contribute to whether there's a cut. As you can say, it's absolutely nonsense for you because you cannot tell me if it's a cut by only using one pixel. But instead, if I describe you with the parts of a cut, for example, the eyes, the nose, the mouth, and the ears, you may be able to give me an answer about what kind of creature I describe to you. So instead, the intermediate layer or the middle layer, it's an representation about different body parts of that animal. Yeah, it's kind of like that. It's like an abstract concept for you to understand a thing. So if you use deep learning with multiple layers, with hidden layers, it can also have that ability of abstract, like human did. Believe it or not, you can take the 3-layer network and continue to stack more and more layers. Some neural networks have thousands of layers, each node playing its part in detecting different configurations of the input data. The rest of this book will be dedicated to studying different phenomena with these layers in an effort to explore the full power of deep learning neural networks. Toward that end, I must assure the same challenge I did in Chapter 5. Memorize the previous code. You'll need to be very familiar with each of the operations in the code in order for the following chapters to be readable. Don't progress past this point until you can build a 3-layer network from memory. Okay, I'll probably do that later after I finish this video. Okay, I'll see you in the chapter 7, which is in another okay. I'll see you in the next video. This is clear.